say what? So it's a great pleasure today to have our very own Duri Andrea Janett here, who will tell us about the truly supercritical trade-offs. Please take it away.
Thanks, Jakob. Yeah, so this is joint work with Susanna, Noah, Jakob, and Shur. And if you have questions at any point during the talk, just ask right away. So to start off with, I should tell you what this truly supercritical trade-offs, what does it mean? So first, let me explain what a trade-off is. So imagine that you have a computational model with two complexity measures, say mu, and you can think of maybe time and space, just for concreteness. And now you will have a worst case upper bound for both of these measures. So I've drawn these dashed lines here to indicate where the worst case upper bound for both of these measures lie. And a brute force algorithm can always achieve like both of these upper bounds at the same time. So the algorithm would lie at the intersection of these two worst case upper bounds. And now if you have a trade-off phenomenon, it would be something like you can optimize one of the measures, but then the other measure will be worse if you are doing that. So for example, this point up here means that you can optimize mu, but you have to pay in terms of mu. So mu will be close to the worst case upper. And now a trade-off result will be these two upper bounds together with an impossibility result, saying that you can never optimize both of these measures at the same time. So it will be noticed by this red box. And in 2016, Alexander Razborov introduced a new kind of trade-off result, where this red box extends beyond this dashed line. So this means that you can approximate, you can still optimize mu, but if you want to optimize mu will be drastically worse. So it will even be worse than the worst case upper bound one. And such a trade-off was later on called to be a supercritical trade-off. So now we know what a supercritical trade-off is, and you will soon also learn what a truly supercritical trade-off is. But first, let's discuss how Razborov obtained such a result. So he established this technique that is called hardness condensation, where you take some input that is already hard, medium hard, and some variables x1 through xn. And now you want to drastically condense the number of variables. And you will do that by substituting each variable xi with an XOR over some new variables, but there will be much fewer of these new y variables. And now you want to show that in terms of the in the y variables, the hardness is nearly preserved, but now you measure this hardness in terms of the number of y variables, which is m, and is much smaller than the number of original variables. And based on this technique, there was a long line of work establishing more trade-offs for different models of computation and pairs of parameters. But one criticism that you could have about this work is in terms of what do you actually measure this supercriticality. So as we discussed before, it's measured in terms of m, and m is the number of variables. But if you look at the actual size of the instance, through this XOR substitution, it will actually blow up quite drastically. So if you measure in terms of the size, you will not go beyond the worst case upper bound in terms of the size. And this has been true for this line of work that I cited before, except for some works that even predate Razborov's paper. So this begs the question, are there truly supercritical trade-offs? Meaning that they are supercritical even in terms of the input size. And this brings me to the result of this paper. So we have truly supercritical trade-offs for different proof systems and combinations of measures, as well as monotone circuits and the Weisfeiler Leman algorithm. This answers open questions in all of these works. And next, I'm going to give you more precise statements of the results teased above, as well as the necessary preliminaries to understand them. So any questions so far? Yes, yeah.
So what is the point of, or like, why is the notion of truly supercritical like interesting? Like, can you give an example of what some of these open questions were, like some applications?
Applications. Oh, so the open question is, for example, you already know that there is a supercritical trade-off in terms of the number of variables, but the instance size increases when you do this transformation. So the question is there a truly supercritical trade-off? So it doesn't necessarily like have an application beyond just being supercritical in terms of the input size, but actually for the monotone circuits, it is necessary to get a truly supercritical trade-off in proof complexity to be able to lift it to circuit. So that's one application. Okay.
Do you have an example of some supercritical for like the time versus space or something?
Yeah, let's say
maybe repeat the question.
Yeah, so the question was if there's an example of concrete parameters in time and space that would be supercritical. So if you could do something always in linear space and also in polynomial time, but to achieve polynomial time, you need like superlinear space. That would be like a setting of parameters. I don't know if this like, I think there's no concrete example outside of proof complexity.
Okay.
All right. So let's move on to the preliminaries. So we're going to work with this resolution proof system where we are given a unsatisfiable CNF formula, and our goal is to prove that is in fact unsatisfiable. And such a proof of unsatisfiability will be called refutation. And to do this, we have just one rule that we can use, the resolution rule. And it says that if we have two clauses already derived, T or X and D or not X, then we can derive from these two D or C or D. Yes.
Sorry, I'm thinking slowly, but just to address the question. So, I mean, there are, for instance, lots of work on Turing machine trade-offs for satisfiability, right? We don't have a priori, for all we know, you can solve SAT in linear time, but then you can try to say, okay, can we at least rule out that you can solve SAT in linear time? And I don't know what the parameters are, like square root n space or something like this. And what the proof complexity gives you is if you're willing to look at weaker computational models, but still fairly strong, like strong to capture state-of-the-art SAT solving or strong enough to capture Gromner basis computations or something. Well, in those settings, the proof complexity trade-offs actually give you exponential kind of trade-offs between running time and memory usage.
Right. So we have the resolution rule. Let's see an example of how you would prove something using this rule. So suppose the initial formula that we are given contains all of these clauses. Now we see that the first two clauses contain X. The first one contains X and the second one contains not X. So we can resolve these two clauses over X, derive this slightly larger clause. And now we see that here we have that, but we also have the singleton clause not set. So we can get rid of set by resolving with this clause. And similarly for Y, W, and U until we arrive at the empty clause. But the empty clause doesn't have any satisfying assignments. And because the resolution rule is sound, we have now shown that the initial formula also didn't have any satisfying assignments. And for resolution, we're going to be interested in the following complexity measures. First of all, size, which is just the number of clauses in your proof, or if you view it as a DAG, as on the right-hand side, the number of nodes in the DAG. The width, which will be the maximum width among all the clauses appearing in the proof. And the width of a clause is the number of literals in it. So here, this is the widest clause that we have. So the width of this proof is 4. And the depth will just be the depth as in a DAG, so the length of the longest path net. And one subsystem that we're also going to consider is when we restrict the DAG to be a tree. So actually, in this example, we have a tree-like proof, and this is what we're going to call tree-like resolution. And since we're going to consider supercritical trade-offs, I should also quickly mention what are the worst case upper bounds on these measures. So for size, we have exponential in the number of variables. For width, it is never more than the number of variables, and for depth, it doesn't need to be larger than the number of variables as well. So our results for resolution are as follows. We exhibit a family of CNF formulas that can be refuted in small width polylogarithmic in n. But if we try to approximate this small width within a factor, say 1.9, then we need to have supercritical depth, which is superlinear in size of the formula. We get a similar result for size versus depth, also for resolution, meaning that we have formulas which have a somewhat small size proof, but getting close to this minimum possible size requires supercritical depth. And then for the subsystem of resolution that I discussed before, tree-like resolution, we also get size versus width, meaning that there are formulas that can be refuted in small width, but getting close to this minimal width requires supercritical size. And the main gist of all these three results is that they are all supercritical in terms of the input size, which wasn't known before for these combinations of parameters. So another proof system that we will consider is the cutting planes proof system. Now we reason with integer linear inequalities. So we can translate the clause into an inequality as shown here by just, if a literal appears negatively, we add 1 minus x on the left-hand side, and it's positively just the literal directly. And we have the following derivation rules. First of all, addition, meaning that we can add inequalities. Multiplication, so we can multiply inequalities by positive integers. And division, where we divide, but we round up on the right-hand side. And this is sound because we are working over the integers. So getting back to my example proof from before, we can translate our clauses into inequalities and essentially do the same proof as before, just by using addition instead of resolution. And now our contradiction won't be the empty clause, but rather the inequality that 0 is greater or equal to 1. Again, we're interested in measures size and depth, which will be, as for resolution, size, the number of nodes in our proof when we view it as a DAG, and depth, the length of the longest path in that DAG. And the worst case upper bounds will again be exponential in the number of variables for size and linear in the number of variables for depth. Okay, now with the two proof systems that we're going to consider at hand, we also need some formulas to work with. And so that's why I'm going to introduce to you the Zeithin formulas, which are one of the main workhorses in propositional proof complexity. So these formulas encode the handshake lemma for graphs. So given a graph and some 0, 1 labeling of its vertices that adds up to an odd number, we will put one variable for every edge in the graph and then have the following constraints saying that for every vertex, the variables of all the edges incident to it add up to the labeling of this vertex. And now, because our total labeling was odd, but the handshake lemma says that the sum of all degrees must be even, this formula, these constraints will be a contradiction. So as an example, let's consider this 4-vertex graph over here. So for every vertex in the graph, we get such a constraint, and then this we will expand into clauses. So on the top left, we have the constraint xa plus xb is 1 mod 2. This leads to the following two clauses. Similarly for the top right vertex. Now, because we have 3 incident edges, we'll have 3 variables and 4 clauses. And then similarly for the other 2 vertices. And as I said, initially, this formula has been extensively studied in proof complexity since it was introduced by Zetin. In particular, it has been used to prove exponential size-level bonds for the resolution proof system, and has also been used to prove low bonds for other proof systems such as sum of squares, bounded depth variance. So one long-standing conjecture in proof complexity was that Zetin formulas are also exponentially hard for the cutting planes proof system. However, this has been recently refuted when Dadouche and Tivari showed that there are polynomial size cutting planes refutation of these formulas. It is also known that cutting planes requires linear depth to refute Zetin. And if you look at these proofs that they exhibit in that theorem, they actually have supercritical depth also quasi-polynomial. So these facts taken together lead us to the question if maybe Zetin formulas would immediately give a supercritical trade-off for cutting planes in terms of size versus depth. One first work towards this result was the supercritical trade-off that is supercritical in terms of the number of variables for cutting planes. Showed also recently. Our result for cutting planes is a truly supercritical trade-off for size versus depth. So again, we exhibit formulas that can be refuted in small-ish proofs, namely quasi-polynomial in the size of the formula, but acquiring this minimal possible size requires you to push the depth beyond super-polynomial in the size of the formula. So this is also supercritical in the input size. However, I should clarify that this does not resolve the question about Zetin formulas. So these are different formulas that we construct, but we start with Zetin formulas to construct them. Okay. So moving on from proof complexity to circuit complexity, we're going to study monotone circuits, which are Boolean circuits with only and OR gates, so no NOT gates, and they compute Boolean functions with n input bits. And again, we're going to consider size and depth, where size now is the number of gates in the circuit, and depth, again, the length of the longest path. And the worst case upper bounds are for the size exponential in the number of inputs, and for the depth linear. There has been some previous work for size depth trade-offs for monotone circuits, namely a non-supercritical trade-off, saying that if you want to, you can be in linear size, but if you want to achieve this linear size, you need almost linear depth. And our result for monotone circuits says that there are, in fact, functions on n variables that can be computed in small size, namely quasi-polynomial n, but achieving this minimal possible size requires the depth to become supercritical, and we super-polynomial. Okay, so any questions about the results and the preliminaries? Then this is as much as I'm going to say about the results. And so now I want to give you a bit of an overview of the proof. The proof is structured into 2 parts. First, we're going to prove a base result, which will be our width depth trade-off for resolution. And then in the second part, we're going to use lifting theorems to get all the other results that I've stated before. Okay, so let's start with the base trade-off. So just to give you some parameters to keep in mind, I have a slightly more precise statement of that result here. So we have a formula of size S, which is roughly n to the c, that can be refuted in width k or approximately k, but getting close to that with k requires supercritical depth. All right. So the very high-level overview of the technique that we use to get this result will be a variable compression, which was introduced by Grohe, Lichter, Neuen Schweitzer very recently. And so I want to go back to one of my first slides where I showed you this Rasborov hardness condensation and kind of contrasted that. So instead of substituting every variable with an XOR of new variables, we substitute directly with the new variable. So we take much fewer variables y1 through ym than the ones above, and now we just plug them into the variables above. Of course, this is going to lead to a lot of collisions. So, for example, you can see that ym goes to both x3 and xn in my picture here. And this will be done in a very structured way. Right. And so we're going to do this kind of variable substitution to Zetin formulas, namely Zetin formula on a cylinder. So our instance is going to be a long, skinny cylinder where we take the edges to wrap around vertically, so not horizontally. And we will have only one odd charge, like the vertex on the top left will have a 1 and everything else will get a 0. So how are we going to compress this? So we're going to first split our cylinder into 3 parts with a very long part in the middle and 2 small ends. And then we're going to identify vertices on the same rows. This we're only going to do in the middle part. So in the middle part, we're going to start on every row identifying vertices in this row according to some modulus chosen for every row differently. And the parts on the sides we're going to leave untouched. This equivalence class on the vertices will then induce an equivalence class on the edges, which we will then use to define our substituted or compressed instance. Namely, we're going to have for every vertex equivalence class now a constraint as before in the Zetin formula, where we say that for all edges that are incident, edge equivalence classes that are incident to this vertex equivalence class, we sum over all variables for these edge equivalence classes, and we require that is equal to the charge of this variable. So namely 1 if and only if it is be 0 up here and 0 everywhere else. So let us maybe zoom in between 2 rows to see like what is this really going to look like on the graph. So I have 2 rows drawn here. The modulus for the top row is going to be picked to be 6 and the bottom row 15. And then after the compression, the rows are going to have much fewer vertex equivalence classes than they have vertices above. And one thing to note is that all the edges that have the same color down here are equivalent. So there's going to be one variable for all of these edges. Okay. So how would one analyze such an instance? Let's take a step back and first see how you could analyze the Zetin formulas on the uncompressed graphs. So here we're going to use this game of cop and robbers that was introduced by Seymour and Thomas in the context of tree width. It goes as follows. So you have some fixed number k of cops, and the robbers start somewhere. And in each round, the following things are going to happen. First, one cop is going to go into the helicopter, and then he's going to point out to the robber where he intends to land at the end of the round. Then the robber has time to move. But you have to move in such a way that he doesn't run into any of the cops. And finally, the cop lands there where he indicated that. And the game ends when the robber is caught, meaning that the cops managed to land on top of it. And so it has been known that this game on the graph roughly corresponds to the resolution refutation of the Zeiting formulas on the same graph. And the number of cops that are playing will correspond to the width of this refutation, approximately, and the depth will correspond to the number of rounds. Okay. So what are some upper bounds on how fast the cops can catch the robber? If there is only k+1 cops, well, they can only use a very simple strategy. Namely, they form a cut in the middle of the graph, and then they start marching towards the side where the robber is currently on. This will take them roughly the number of vertices in the cylinder many rounds, so k times L. And this then translates into a resolution proof of width k+3 and depth k times L. So the k+3 here comes from the fact that the correspondence that I showed before is only approximate. If we have much more cops, say 3k cops, we can be a lot more efficient. That way we can do some sort of a binary search strategy where the cops cut off in the middle, then they check where is the robber now, then they slice that part in half and so on. So they catch the robber. And this takes, well, k times log L many rounds, so it translates into a resolution proof of width 3k and depth only k times log L. All right, but now we don't want to analyze just the instance on the uncompressed graph. We want to analyze the instance in the compressed graph. And so we also need to have a compressed game. So here, rather than just the cops occupying one single vertex, they will occupy the entire equivalence class of vertices that they stand on. So whenever a cop is at the vertex, it will get a clone on all the vertices that are equivalent to this vertex. And now let's fix the number of cops to be k+c. Again, the robber starts at some fixed vertex. The cops will mostly play as before, namely like one cop gets into the helicopter and signals where he will land. And then the robber has to do a special move now because he doesn't only have to avoid like the real cops, but also all of their clones. And on top of that, he should own, like if he takes some edge, then he should also take all the edges which are equivalent to this edge, just to respect the equivalence relation that we put on the graph. And finally, the cop will not land just at a vertex, but also the entire equivalence. Now, what can we say about this game? Well, the cops are, of course, very happy. It's much easier for them now. In particular, the strategies that I've shown you on the slide before work without changing anything because they can just ignore the fact that they also have their clones and play as before. So we'll get exactly the same upper bounds. But for the robber, of course, life gets much harder because he has to do these very special moves to avoid all the clones. And so it will be much harder to prove the lower bounds, actually. And we will still be able to show a strategy for the robber, and we will consider a very special type of move, which I will show you next. So the robber will constrain himself to only use the moves where he moves on at most c+1 adjacent rows. And then he does a move for some distance, making sure that he ends up in the same row as he started, and then just copies this periodically according to some fixed period, which will be the GCD of the moduli on these rows. All right, so with these moves at hand, we now can devise a strategy for the robber where he will play as follows. So if you remember, we left these small parts on both ends untouched without any compression. And so the robber will use this, and he will always stay on either of these parts. And then whenever necessary, he will switch sides to the other part using such a compressible move that I've showed you. The only problem that he can run into is that if the police start blocking off the middle part, so he cannot freely slide to the other side. However, the rover is very foresightful and smart, and so he can deal with this, and he does this by keeping away not just from all the actual cordons that the cops are forming, but he considers some kind of more general notion that we call virtual cordons, which is a kind of a closure of all the cordons that the cops could be forming within the next step. And keeping away from these virtual cordons allows the rover to escape in time. And because these cordons can only move very slowly, even if the police decides to form a cordon and move it towards the rover will manage to survive for many rounds. Namely, we can show that the rover survives for n to the k rounds against k plus t many cops. So n to the k will be roughly the length. Yeah.
How do we know there's not like cordons everywhere?
Well, this is because we only play against somewhat few cops, so k plus. And it's like that the identified vertices are still somewhat far apart with respect to this k plus c. So even if they decide to form a cordon, there will be many copies of these cordons, but there will be ample spacing. So they cannot somehow move the cordon and then suddenly jump to the next.
But this is part of the technical meat of the paper. It's a very good question.
Okay, yeah.
It's far from obvious.
Any more questions to the? All right. So just to provide you the full information on the construction here, a short slide on how we choose the moduli. So if we fix k and c, so k, if you remember, will be the number of rows, c will be kind of the number of extra cops that we let play, and we pick k many co-prime numbers, which are roughly of size n. And these are guaranteed to exist by the prime number theorem. And then we just, for every row, pick some subset of these co-prime numbers and take the product of them to be the model. And now, because we take c plus 1 many of these co-prime numbers, pi, the size of the product will be n to the c plus 1. This is, however, much smaller than n to the k, so the lower bound will be supercritical. Okay, so getting back to the motivation for this work of Grohe et al. That we are heavily building upon. So this paper was actually about the Weisfeiler Leman algorithm. And so this is an algorithm that refines colorings of a graph and can be used as like a graph isomorphism test. And there are two parameters that you're interested here, the dimension of this algorithm and the number of iterations. So the dimension of this algorithm forms a hierarchy somehow in the sense that the higher dimensional the algorithm we take, the more expressive it is, the more graphs it can distinguish. And so what GLMS showed is like the first superlinear lower bound on the number of iterations for any dimension. So they showed that for fixed k, there is a graph pair that can only be distinguished by k-dimensional Weisfeiler-Leman after n to the k half iterations. And how does this relate to the results that we have? So the dimension of the Weisfeiler-Leman algorithm on some working on a graph is roughly corresponding to the width of a resolution refutation of that Satin formula on that graph. Similarly, the number of iteration roughly corresponds to the depth, and from the way this graph pair is constructed, we can extract the Satin formula. However, the correspondence between dimension and width is not quite exact, which is why this result is not robust enough to yield consequences in proof complexity. But with our more robust version of the result, we can also get something for Weisfeiler Leman, namely saying that there are graph pairs which can be distinguished already at dimension k, but up to dimension k plus c minus 1, we require many iterations. So that's it for the first technical part. So let's move on to the second technical part, where we're going to use lifting to go from resolution, depth, width to all the other results that we have. So what is lifting? Lifting is the idea to use composition to relate different models of computation. So let's say that F is some instance that is hard for some model A. Now we want to compose F with some gadget G such that F composed with G is hard for some model B. And usually it will be that A is a weak model and B is a stronger model. So to put this very abstract description a bit more concretely, as an example, we could hope that if F requires large resolution width, then we compose it somehow to get a new instance that requires now large resolution size or cutting plane size or monotone circuit size. In particular, this G that we're going to compose with is the indexing gadget. So we want to take a function on n input bits and compose it with the index function. The index function has like split domain. So the numbers 1 to m times the bit strings of length m, and it can be viewed as follows. So let's suppose Aleph gets the first half of the input, which will be a number between 1 and m, and Bob gets a bit string, gets the second half of the input, which will be a bit string of length m. Now we just consider Alice's input as pointing to one position in Bob's input, and then the output will be the value of Bob's input in this position. So in particular here, Alice gets 1, so she points at the first position in Bob's string, so the output will be 0. But now we want to do this not only for 1 bit, but for a function that takes n bits. So we have to do this n times. So Alice gets n numbers between 1 and m and points. So this will be n pointers to Bob's n bit strings of size m. And then this will give us the input that we're going to feed to her. So for example, here in the second position, Alice gets 3. She points to the third position in Bob's second string. He has a 1, so the second bit that we feed F will be 1. Of course, this is only for functions, but there's a straightforward way to generalize this for CNS. So we want to go from resolution to monotone circuits. And for that, there's this previous work of Grach, Kamat, and Sokolov. They show that we can lift a resolution with depth trade-off to a monotone circuit side depth trade-off. So namely, they have the following theorem, saying that from a formula F, we can construct a function, little f, such that a size m to the w depth d monotone circuit for little f implies the existence of a with order w depth order d w resolution tool. Okay, so if there is a trade-off in the model down here, we can now apply this theorem to get a trade-off for monotone circuits. One crucial issue, however, is that the number of variables in the function little f here will correspond roughly to the number of pauses in the formula. So this is the reason why the previous work on supercritical trade-offs, which was supercritical only the number of variables, didn't work to get this kind of a result. So in fact, we need a truly supercritical trade-off to start with. However, for our purposes, we have this trade-off that works between a constant and k up to k plus c. So we have to be very careful about these Landau notation up here. And in fact, just taking this theorem as a black box doesn't work for us. We need to prove a tighter lifting theorem. So what is the the tightest possible lifting theorem that we could hope for, it is essentially removing the big O notation here entirely. So from size m to the w depth d monotone circuit, extract with w depth d resolution. Now that seems somewhat ambitious. So as an intermediate goal, let's see if we can prove this for resolution proof above. So a size m to the w depth d resolution proof implies a width w depth d resolution proof for the non-composable. And indeed, we were able to do this almost, except for this, this m half to the w rather than m to the w. So this is essentially optimal, and the proof is rather simple via random restriction. And from this, we get as a corollary our size depth trade-off for resolution. For monotone circuits, we also managed to prove a tight enough lifting theorem so that we can apply it, namely from a size m to the 1 minus epsilon w depth d monotone circuit, we can extract that with w depth wd refutation for the uncomposed problem. It's also very close to optimal, so up to the 1 minus epsilon factor here in the exponent, and it also applies to cutting planes and monotone real circuits. So both the results for monotone circuits and for cutting planes derive to statistically. Yeah, as I said, as a corollary, we get the monotone circuit size depth trade-off as well as the cutting plane size depth trade-off. Finally, we also prove a new lifting theorem for tree-like resolution to get our result for tree-like resolution. Here we show that size S with W tree-like refutation for the composed problem, where note that we're now not using the indexing gadget, but rather the XOR gadget. This implies that there is a depth log S with W over N, a refutation of the uncomposed problem. And one important thing to note here is that the width is also reduced. So not just size to depth is a reduction, but also width. As before, as a corollary, we get our size depth, size width trade-off for tree-like. So one more thing that I should mention, maybe just about the technical part. So this is the end of the second technical part. Are there any questions here? Or so the thing that I should mention is that there has also been some concurrent work actually by Gus, Meister, Lichter, and Sokolov. And they also obtain size depth trade-offs for monotone circuits and cutting planes. And they use the same kind of strategy to obtain these results. So they prove first a depth width trade-off and then lift it to these results. However, their base depth width trade-off is completely different. So they introduce a new formula that formalizes an interesting combinatorial principle. This immediately gives them a very robust trade-off. So they can use the existing GGKS lifting theorem as a black box. By contrast, our work achieves some slightly different parameter regimes, where namely we get a formula that can be refuted in constant width. And we also get results for the Weisfeiler Leman algorithm. We continue the study of this compression technique introduced by Grohe et al., which we find worth investigating further. And the tighter lifting theorems that we prove by necessity might also be of independent interest. Okay, so to wrap up, let me give some overview of some open problems that we leave. So first of all, we would be interested in further applications of this compression technique in proof complexity. So one question is, can we like do some such compression to other formulas, for example, pebbling formulas, or can we find other graph compressions to put into this compressed Satin framework? Of course, it would also be interesting to have more supercritical trade-offs for other proof systems or combinations of measures. So, for example, size versus space, or maybe the polynomial calculus. And one more thing that would be nice in the same regime that we are working is if you could unify the parameter ranges from our work with the concurrent work. So get a very robust trade-off that starts kicking in at constant width already. And then perhaps a bit more ambitiously, the next two problems. So as I already used to motivate the results of this paper, what is actually the complexity of taking formulas for cutting planes? Like, is there a supercritical trade-off? Yeah. And then a similar story also occurred for the perfect matching function for monotone circuits. So this was one of the original functions for which there was a lower bound known, a super-polynomial lower bound shown by Razborov. And it is also known that the linear depth is necessary. I think they got the year wrong on the citation. However, this super-polynomial lower bound, in contrast to other lower bounds in this paper, was never improved to exponential. So is it possible that there could be a supercritical trade-off for the perfect matching function? All right, so to conclude, I have shown you our results, which are truly supercritical trade-offs with meaning in terms of the size of the input for different proof systems and parameter combinations, as well as monotone circuits and Weisfeiler Leman. The proof goes via lifting a base result, which will be the depth versus width trade-off. This we obtain from compressing a taking instance and then analyzing it via coprolog game. And to be able to lift, we also need improved lifting theorems. And summarizing the directions for future research, can we find more applications of compressions, more supercritical trade-offs, and perhaps more interestingly, what is the complexity of taking formulas for cutting planes and perfect matching for monotone circuits? I thank you for your attention and be happy to answer any questions.
Questions for Duri? On any topic, right?
So this compressed cycle was still cycling, right? It was still cycling at that point. So where did it stop being cycling?
No, it stops being cycling once you do the compression, because it's so you take the original Zeitling formula on the uncompressed graph, and then you substitute according to this edge equivalence.
Isn't that the same as identifying vertices or something?
There's more edge equivalence.
You can go back to the picture.
You want this one or this one?
So yeah.
I mean, here you could think that like there is a constraint where this edge variable appears like 4 times, but that's not the case.
Yeah.
So it's just the way that I stated it is true because you still have the constraint for every vertex, but it just happens that at every equivalent vertex, the constraint will be the same.
So let's thank Duri again. Continue here. We are back after the break and will be on the board. And Duri will go over some of the technical details of the talk.
You said they have a son?
What? We should have this room until 4.
But yeah, I think I booked this full seminar.
We have it booked until 4 according to our administrator.
But I booked. I think it's
Yeah, you should double and triple check. I'm pretty sure we have it until 4. So here's the second attempt we're making of starting the second half of the talk. We're defending the room against aggressors, and for as long as we can, we'll keep the room. Someone will, lock the door and block any intruders, while Duri will tell us about technical details of the paper. Thank you.
Yeah, thanks, Jakob. So let me tell you maybe the plan of what I want to show you, and then we can see how much of it we get through. So first, I will give the details of the construction. And then we'll set up definitions plus lemmas to prove the main theorem, which is the rubber strategy to survive many rounds.
So we try to get the blinds down. I think there's a lot of glare on the board.
Then I will sketch the proof of the main theorem.
Okay.
And if we have time and energy, maybe I will sketch some of the lemmas. So, for the construction, I want to fix some parameters first. So let's k be at least 2. This will be the number of rows. C between 1 and k minus 1. And n at least bigger than 4k plus 2, but also large enough such that there are k co-prime integers p1 through pk between n and 2. So the existence of such a large enough n is guaranteed by the prime number theorem. Then we will set L to be 2 times k plus c, and then the product of all the vectors. So I pick the box. And we will set R to be k plus c plus 1.
But what are the bounds on? So k, we should think of k as like logarithmic in n, or how large can k be?
Like right, it's k like from constant to up to like n over log n.
Oh, okay.
Like this. Just also to conform with the prime number theorem.
Mm-hmm.
So want to look at a cylinder as follows. have this wrap around here, of course, and all of these edges. And now here the left part will be of size R, the middle part will be of size L, and the right part will again be of size R. This is also what I'm going to call these parts of the graph. So left part, middle part, right. So, as alluded to during the first half, we will now put an equivalence class on the vertex set of this graph. So for each row, the modulus mi be set to be 2 times k plus c times pi, and then the product, all the factors up to pi plus. And this with cyclical wraparound. So if I'm on the bottommost row, I will take this and then the first c factors. And then we will say that on the same row, IA and IB, so a vertex IA, where I is the row in which it is and A is the column, will be equivalent to a vertex IB. So note that I only identify vertices of the same row if A and B are in the middle part and A minus B is congruent to 0 mod M. So now we want to extract from the vertex equivalence an equivalence on the edges. So we assign some labels up, right, down, left, just in the obvious way to all incident edges for every vertex. And then we say that edges E1 and E2 are equivalent if they start from an equivalent vertex and they are labeled with the same label. So if EI is V1, W1, E2 is V2, W2, V1 is equivalent to V2, and EI, E2 have same label in or with respect to V1, V2. And now, to get this to be an equivalence relation, take transitive flow.
Can you say more exactly what this means in the context of this particular graph?
Yes. I'm just about to make some remarks. Give you some more intuitive picture of what this means. So first, well, the vertices in left and right parts are like singleton equivalence classes. Secondly, in the middle part, on every row, I, there are MI equivalence classes. I can spell them out if you want. It's just for every.
There's a question in the chat. How we deal with exactly like the borderline between the left and right part and the middle part? I mean, so we just use those definition and
Yeah. So in particular, the edges that cross the border will be identified with many edges in the middle part.
Okay.
So regarding the edges, horizontal edges and vertical edges are only going to be equivalent to the same horizontal or vertical edges. So there will be edge equivalence classes for horizontal edges on every row, and then between any two adjacent rows, there will be edge equivalence classes for vertical edges.
And is it correct? It's like horizontally, things are fairly straightforward, right? Because you just, every MIS edge will just be the same and nothing fun happens. But like between two rows that have different moduli, then weird things going to happen. And actually, edge equivalence classes are basically going to look like complete bipartite graphs, like in the example you had in the first half. Is that right?
Yeah. So I'm going to say
you're getting there, I guess. Sorry.
There are. So well, I mean, the picture with the complete bipartite graph is also helpful. I'm just going to say how many there are. So for every row, we have MI horizontal. That's, the edge equivalence by just the equivalent symbol with an E. And for rows I and I plus 1, there are GCD of MI and I plus 1. Vertical. So every such class corresponds then to a complete bipartite graph, as you mentioned. I'm gonna switch to this side if it's possible. Okay, so now I can define the compressed taking instance. So I'm not going to define it in full generality, but rather specify it to our particular graph compression. So take, by the way, let me call our cylinder just G from now, because it's the only graph that I care about right now. So take just the regular Satan formula on G with only odd charge at 1, 1. And then substitute the variables by sending xe just to x, and then a variable for the edge equivalence class where, so this is one variable for every. So how big will this formula be? Because I mean, after all, we're interested in supercritical trade-offs. So the first thing that we should check, or like truly supercritical trade-offs. So the first thing that we should check is that our lower bound will actually be truly supercritical. So the formula has so there are size of the set of vertex equivalent. We have equivalence classes, many constraints, and because we have degree 4 at every vertex, every such constraint will lead to 2 to the 3 clauses. So it has 2 to the 3 times size of the set of vertex equivalence classes, many clauses, and this is k squared n to the c plus 1. Yes, 2 to the c plus 1 if you want to be very precise.
It's kind of a trivial remark, but it's important to note that so every Satan constraint is talking about edges incident to a vertex, right? And then the way you set this up, once you identify 2 vertices, like all the edges for these 2 identified vertices are also identified. So that's why you get this massive collapse in the number of sort of quote unquote Satan constraints. Like a trivial observation, but it's kind of a nice observation.
So next I want to define the cop-robber game, and I guess like we had it like twice during the talk, so maybe I just defined a special move, and we know that the cop gets a helicopter and he's safe and blah blah blah. So possible move from vertex W1 to W2 is a subset of the edges graph satisfying three conditions. So M must be closed under Janett. Edge equivalence class relation. Right, so if I put one edge into my move, then I have to take this edge everywhere it appears on the graph. Or I have to add all the edges that are equivalent to it. The cops, and I will denote composition by blackboard C. Do not stand on any vertex that is incident to any of the edges that I take. So this just means that I don't run into the couple. And finally, we want to enforce some kind of parity flip. So particularly, we want for every vertex that has an incident edge inside of the move, its degree is odd if and only if it is the first or the last vertex. So if and only, like, the only vertices in the graph that have odd degree in my move set will be the ones between which I move. So with this game, with this definition of compressible move, we are then able to show the following lemma, connecting the Copenhagen game to the resolution reputations of the compressed safety problem. So with W depth, the refutation formula implies that W plus 1 pops can catch the rubber or can win in D plus 1 rounds. And now about the cup rubber game and our instance, we can prove the theorem that the rubber can survive L minus 2R over 8 times K plus E, which is omega of n to the K, rounds against K plus C cars. Okay. And so now from this theorem, together with the lemma that I've written above, we get the claimed supercritical trade-off. Because look at this remark and just all right. So now, I guess yeah, one thing that we can certainly have time for is like see the definition of this virtual coordinates, and then yeah, maybe see how it plays into the proof of this theorem. So for that, I have to set up a bunch of definitions for so
The chair and the computer are starting to get in the way.
So I want to define something called a periodic path, and then from this kind of path, we can then get compressible move, which is essentially exactly what I had on this slide, where the move is like red, and then it is just repeated, right? So take some subset, non-empty subset I, the rows. And some columns A and B. And we set GI with a GCB of the moduli of all the rows in our set. So a periodic path is a path.
And we think of these as contiguous, right? You said this. Or?
They don't need to be
contiguous.
No. But I mean,
When you use it, it's always
yeah.
contiguous.
Periodic path can be obtained. So I just define a periodic path to be any path that I can obtain in the following way. So a simple path between A, so A is a column, and A plus GI, starting and ending in the same row. And then extend it horizontally until you first hit your column B. So this will be then an I-periodic path from column A to B. I'm leaving away one small technical condition in this definition, but we are going to need it for the purpose. So the remark that I already kind of included is that I-periodic paths between left and right parts give compressible moments. Just as well, by picking this GI to be when it repeats, for sure we are respecting the edge equivalence class And then, well, if we avoid the count. Yes. And the parity flip is satisfied because there is no identification in the left and right file. So take W, a subset of the vertices, and denote by Wx just all the vertices in V such that V is equal to equivalent to W for some W in W. It's just setting up some notation for the next couple of definitions. So W is a vertex separator. I times A comma B, where I will be a set of rows and A, B will be some columns, such that A is smaller than B. If there is no path avoiding W A to B in G restricted to so W is said to be I separating. If there is no I periodic path. From the first column to the last column. In the graph restricted to this set of rows. And W is set to be A separating, where A is a number that we can fix. If it is I separating, for all I with size between 1 and 8. Yes, I almost move back over here and just check most of my. Now, just to interject a minor proposition. So we're going to skip the proof of. So if S is a minimal vertex separator, for B, then the diameter of S will be at most the size of S minus 1. Okay, what do we mean by minimal? We just mean minimal with respect to set inclusion. And diameter will just be the difference between the first and the last row at this set. And so, column, of course. So why is this proposition true? Like if this set S were more thinly stretched, then there would be a column somewhere in the middle where there is nothing, but then it has to separate either already on the part left of this column or on the part to the right of this column. Okay, finally, I can define a virtual cordon. So, given a set of vertices W and a vertex separator S or G, so this separator S is said to be a virtual cordon of W if the following two conditions are true. So on every row, the number of vertices of S in that row must be at most the number of vertices of W in that row. And on the unique rows of W, so on the rows where W has exactly one vertex, then we have Sj is actually contained in the vertices which are equivalent to that vertex of W in that row. Really the key definition in the analysis, and then we will say that a set W of vertices is critical. Where we really mean critical to the robber, if it is C+1 separating and it has a virtual code. Everything is clear so far, then I'll need to state two more preliminary results before we can get to the proof of the theorem.
Do you want to say, I mean, criticality seems like a key notion, right? Do you want to repeat again, explain to us what this means?
So criticality is just the notion that we're gonna use. So like if the cops occupy a critical set, then the robber is really in danger. And in particular, C+1 separating means that there are no very simple, like there's at least no aperiodic moves for like some very small period or like period size of more. Yeah.
Because we have the way we're thinking about robber strategies is we're going to do these periodic moves that involve at most C+1 rows.
Right.
And you're saying basically that there are no such good moves. the cops are maybe not cutting off everything, but any segment of C+1 rows, they're actually cutting that off. So the simple moves that we want to choose, because we can analyze them, we're going to be screwed. Okay, that's item 1 and item 2.
Item 2 is just this kind of virtual cordon exists, so the cops can potentially within the next round occupy something that really cuts off the diagram. In particular, I should say about virtual cordons that like a vertex, like if W itself contains a vertex separator, that is also a virtual cordon. So virtual cordons is really even a more general notion than just the vertex separator of W. We have the following proposition for a set of most k plus c vertices that is one separating we have that any two minimal virtual cordons of W coincide on the unique rows of W. And the proof of this really heavily relies on the fact that the way we chose our parameters and this kind of picking the the subsets of the factors in this kind of way that is very overlapping for adjacent rows. But I'm not. I don't think I'm going to have time to show this proof. But what the proposition tells us is just that if there are many virtual coordinates for some composition, still they on the unique rows of the composition they are fixed to be at a certain place. And so in particular, because we will always have at most k plus c many cops, meaning the set W will be size at most k plus c, there will always be some unique rows because we picked c to be smaller than k minus. So the key lemma that is going to allow the robber to do this kind of foresightful strategy, like he knows in advance when a virtual coordinate is going to appear. It's as follows. So if W is critical, of course, again, of size of most k plus c, then if we take some subset W minus that is just W with one vertex deleted, so size of W minus is size of W minus 1. And if W minus is C plus 1 separating, so again, as Jakob mentioned before, this essentially means that our like somewhat simple loops won't work. Then we can show that W minus is free. So what does this tell us? If going from W minus to W, the position were to become critical, then, so it goes from non-critical to critical, then it couldn't have been that W minus was C plus 1 separating. So in particular, we would have had a move to move away once this critical set appears. Okay. So I think, yeah. Maybe.
Did you say this? Sorry, maybe you said it a little, but the rubber plan is somehow we have these uncompressed ends, right? So we're going to stick around there, and then until a cordon appears somewhere, and then we'll try to be at the as far away, left side or right side, whichever side is further away from the cordon. And you're now saying that we sort of have some advance warning so that we can move.
Yeah. Right.
To the good side.
So now I'm going to just spell out the rubber strategy in some more detail. And this will then prove our main theorem, well, up to all the lemmas whose proofs you can see. So so you note by CT minus CT plus the Cope positions throughout the game. In particular, in round T, the position with the Cope in the helicopter will be CT minus, and the position once the Cope has landed will be CT plus. Okay. And now the rubber will keep some invariance. So this is some invariants that are going to guarantee that the rubber hasn't lost yet, and we're going to show that he will be able to maintain these invariants for many rounds. So the first one is that the rubber is on a Cope-free column. In right or left part. So this essentially guarantees that the rubber didn't lose yet. And the second one will be that if the position with the Cope in the helicopter is critical, any minimal virtual cordon of CT minus has horizontal distance at least L half minus 4K plus C times T from the rubber. I should say invariance in round T. I should click. In particular, I mean, well, we can plug in here how large can T be for this thing to still be positive, and this will immediately give us 0. So what we want to show that the rubber can maintain I1 and I2 for L minus 2R over 8K plus C rounds. And then we'll show this one back. And the induction on the round. And so T equals 1. The base case is very simple, because actually in the definition of the game, all the cops start in the helicopter. So there's no cops on the graph. In particular, E minus 1. All right, so going from T to T plus 1. We will do a case distinction. So first case, what if CP plus is not critical? So invariant, I don't know how visible everything is, at least for the camera, probably not here. Invariant 2 will just hold because well, we have that C T plus 1 minus, in particular a subset of C CT plus, because it's just CT plus with a vertex, with a cop lifted. So it will also not be critical. And for invariant 1, we just need to ensure that we can actually move. But so here there are 2 minor subcases. So if so in particular, we know that it's not critical, so either is not C plus 1 separating. So in particular, there is an I-periodic path from the first to the last column, so we can just move to whichever column we want according to this path. And if you remember, we picked R, the size of the left and right part, to be larger than K plus C. So there will certainly be one cop-free column on both sides. So we can just go wherever we want. And for CT plus has no virtual cordon. So in particular, it doesn't have a vertex separator, so we can just say it on the same point. Okay, for case 2, we want to consider what if C T plus is critical, but C C T minus is not. Then we apply the key lemma, which implies that C minus is not C plus 1 separating. And now we just have to, so this means that we can move to whichever side, and now we just have to be somewhat smart about how we pick the side, right? So we want to use this proposition here to say that like the virtual coordinates of CT plus can actually not be very far spread out. And so this then in turns means that like they have to be far from at least one of the left or right parts. So we just move to the one from which it is far. So maybe let me just say for S prime minimal virtual coordinates of CT plus. We have for every V in S, V prime, and S prime that the horizontal distance in terms of columns between these two is bounded by the diameter of S plus diameter of S prime. This is by proposition. Guess I didn't give it a name. Position 1. And then we have this other proposition over here, which I guess was before, so it will now be called proposition 0, saying that these diameters must be somewhat small. Namely, what bound do we have? Size of S minus 1. So thus we have that it is at most 2 A plus 3. Okay, and now we know that all the minimal virtual coordinates, all the virtual coordinates are going to contain a minimal virtual coordinates, and they're all going to be in an interval of say size 4K or something, and then we just move further away from that interval. And now we just do the last remaining case, and then I guess. So what remains to do is what if C minus is critical? And then for invariant 1, so now we are in the situation where the cops are actually maintaining a critical set. So in particular, they have a virtual coordinate. So they are like potentially about to cut us off. So we just want to say that by invariant 2, like they are still sufficiently far away. And we want to say that they cannot move by too much at a time now in this one step. And invariant 1 will just be maintained by moving in the same part, similar to what we did in case 2 if there is no virtual coordinate. And then for invariant 2, now we need again to do such an estimate computation, like very similar to what we did here, to get that we cannot, like this thing cannot shrink by more than this 4 qubits. So I think that's enough for a proof sketch, and I don't know if everyone wants to hear about how to prove the lemmas. I can very well do that, but I will not force you on to that.
Questions, comments, protests at this point?
On any topic.
Where would you go to improve these results? So we're stuck between like K and 2K, are we?
Yeah, so okay, maybe that wasn't mentioned the entire afternoon. Like for 2K, there's a slightly better strategy than just marching towards the rubber. You can like cut off a piece of length, square root of the length of the entire thing at a time, and like that you only need like square root of length of the entire thing around. So yeah, maybe you can show a lower bound between 2K and 3K of square root of length. I guess to really improve it, like come up with some new clever graph compression.
Or do compression for another graph? Or this is the same thing?
Yeah, I guess it's not the same thing, but I don't know. I mean, you said in the break that for expanders, it seems like taking this transitive closure could be a lot, right? But it seems that maybe you have to use.
First interesting question might be, what is the vertex identification now? You choose a subset of vertices in the graph, so ending everywhere, but not the whole set of vertices, so that you make them the class. Even this question is unclear for general experiment. Because after that, assuming that the vertices, let's assume the graph is regular. Then we can perhaps apply the same second step to generate attribute. But for the first step, what is a good choice of this vertex step? It depends on where we're shooting. Because here, it's somewhat clear we're shooting for to simulate this separators, such that whatever virtual coordinates in the compressed thing, actually you can extract from such a thing an actual vertex separator in the original graph, and actually in a unique way. Expand the realm of using analogous goal behind.
Maybe there's some group theory going on here, maybe something based on groups, like graphs, like daily graphs, something based on groups, other kinds of groups. What would be like the dream result, but the dream supercritical trade-off for width versus depth?
In this context, where we're also thinking about Weisfeiler Leman, there is like an upper bound for the iteration number, is something like n to the k or n to the k minus 1. So you can get the lower bound to be n to the k minus 1. I think that would be great. So well, the lower bound is already n to the k, but the actual size of the instance will be still square of that. So if you could remove that.
But to get the width down to like here, I guess you say that if the width is like k plus square root k, then the number of iterations is like n to the square root k. That's roughly what you're getting here. Right? So to get close to the right width, you
You're roughly speaking a factor of two.
to a factor of 2. Okay, so to a factor of 2, you get like a lot left. So what would be but how close should be close? Would it be
I mean, like a dream scenario would be something like if you look at the kind of results you get from Razvorov, and I need some help here, but basically it is you get something like you can achieve, say, with n to the epsilon for some really small epsilon. Okay.
Okay.
But for any width smaller than n to the 1 minus epsilon,
Right.
which is sort of,
Yeah.
you still need like supercritical depth.
Right. Yeah. So this
So
is
like basically that
Yeah.
because with n is kind of you can't go above it, right?
Right.
But already like if you want to do n to the 1 minus epsilon,
Yeah.
then depth will go completely out of the window. That's kind of a dream scenario, and those kind of results. Blanking on the exact parameters now, but for like several pairs, we do have these type of like extremely robust trade-offs
Right.
using Razvorov's hardness condensation technique. And the problem is that when you do Razvorov hardness condensation with these parameters, then also the object, like the input, blows up exponentially. So that in terms of Duri's picture, like if you actually look at in terms of input size, the trade-off is like completely uninteresting.
Yeah. And these kinds of parameters are not achievable at all by this kind of hardness.
I mean, we get stuck up at 2W, right?
That's right.
Or,
Yeah.
or definitely prove it at 3W, you're dead. Definitely, right?
For this kind of instance, but there is no world where one can imagine this with this world. Or
I think the
The
mission
bracket
paper,
that's close to that, right?
But yeah, so the girls had all formulas.
their lower bound is somewhat weaker, it's only quasi-polynomial.
Yeah, but they can go from like logarithmic with.
If they are extremely robust, the lower bound is not exponential. Maybe that's one thing you could try to further optimize. They are robust, almost extreme case.
Any other questions? Let's thank Duri one final time.